survey operation, you're going to create a fixed known mission, okay? So this is back at the main page. When you're on site, the first thing you're gonna do on site is turn the drone on so it can start collecting GPS data so it can identify where it's at. So when you start your flight route mission planning, the map will be the first thing that pops up and it's gonna zoom in right where you're at. Right? So we're gonna create a photogrammetry mission.
Okay.
And we're gonna also copy that and create a LiDAR mission. So I'll show you how easy you can fly both. For the flight route altitude, first of all, I asked you guys, do you know about photogrammetry? Do you understand how photogrammetry works?
Little bit.
A little bit? Nickel tour photogrammetry. All right, I'm gonna kick this out of the way so I don't step on it. So the last thing I'm gonna do is break a prompt on your new drone. Okay. If I have a site that I want to map, the way photogrammetry works, you guys are familiar with like stereoscopic photos, or using photograms, or using aerial photographies with a binocular set to get that 3D. A ViewMaster. You ever played the ViewMaster? No? Am I talking out of my ass here? What? If you have two images that were taken a certain distance apart, it's like your eyes. You get binocular vision, and you can generate a 3D visual view from two photos. The way photogrammetry works are you take a series of photos on a site, and you're building a matrix of stereoscopic images, okay? For each line that you fly, you basically fly a site like you mow a lawn, okay? So you cover the entire site. For your series of images that you're flying, each new image only collects 20% more data. So each new image is 20% more data. So you get a very high stereoscopic view as it's going. The tighter your overlap, the better your model is going to be. Unfortunately, the more photos you have to process and the more complex the model becomes. So there's a fine line where we're going to say, these are the limited number of photos that I have to take to get a really good accurate model without going overboard. Typically that is going to be a 75 to 80% lap going forward, okay? We're also going to intermix those with different flight lines on the next run. This side lap is going to be 70%. So basically for every 4 photos, are going to look like that. So I got 80% this way, 70% overlap that way. And the software that we're going to use tomorrow, Pix4D, basically creates a 3D model network out of this mosaic of photos using a parallax view of different objects to build that model. So with photogrammetry, and again, I'm all self-taught on this stuff. Photogrammetrists are like geodesists. They're in their own little universe. Photogrammetry relies on the drone in the sky with the camera. It's taking a photo of the ground. This distance here is calculated based upon the focal length of the camera. So the camera has a fixed focal length, okay? And has a fixed field of view. And that focal length with the distance, there's a ratio of the focal length to distance that calculates what's called the ground sampling distance. And basically what the ground sampling distance is the representative size of a pixel on a photo, okay? So your final model accuracy is determined by what's called a ground sampling distance, or GSD. I don't know the exact formula. There is a formula. I actually got a slide that has a formula, but I don't know where it's at. But basically, that's why you need a high-end camera with absolutely no zoom and those fixed lens. Those models and all the optical attributes of that lens is built into the model of the photogrammetry software. So the photogrammetry software says, you took these photos with this camera, here's all the model lens information, I can calculate what the elevation is based upon the elevation of the drone. So I have the elevation of the drone with the GPS, I have the focal length of the camera, I have this view, it can calculate this distance and therefore calculate the elevation of the ground, all right? The ground sampling distance is expressed in centimeters, all right? So if you have a GSD, we're gonna fly this. This is what we talk about all the time. For easy math, we like to shoot for a GSD of 1 centimeter. That's not set in stone, and that's per pixel. So centimeters per pixel is the GSD. So if I look on a photo and I can bring that photo up and expand it up and look and see all the individual pixels, each pixel represents 1 centimeter by 1 centimeter square on the ground, times 8,000 times 5,000. So each photo is going to be, 50 meters by whatever, 80 meters, representative at 260 feet. So the final accuracy of your model is determined by this number. On average, horizontal accuracy equals plus or minus 1 to 2 times your GSD. Vertical accuracy is plus or minus 2 to 4 times your GSD. So we can say when we do our models for photogrammetry, and my photogrammetry is calculated out by 1 centimeter per pixel, my final model is going to be plus or minus horizontally 2 centimeters. So I'll be within an inch horizontally. Vertically, 1 to 2 inches, which is not bad for photogrammetry. Old style photogrammetry was maybe plus or minus 6 inches to a foot vertically. It was horrible. All right. So the lower, this GSD is 100% influenced by your altitude you fly at. The lower you fly, the more accurate your final model is going to be, but at the cost of processing. It's almost like an exponential time and size in processing. For flying this at like 150 feet off the ground, my processing time and file size is going to be about 4 times the size of flying at 260 feet. So it depends on how accurate you want your model at. We typically, if we use 1 centimeter per pixel, and we're happy with 1 to 2 inches of horizontal accuracy, it'll take me, I can start calculating it's going to take me X number of hours to process my photography for a model for a given site. Okay, I can usually process maybe a 50 to 100 acre site in about 4 to 6 hours. Okay, if I flew it at 150 feet, it'll be more like 12 to 16 hours for that same model. And my file size is going to be, okay, your biggest enemy when it comes to photogrammetry and LiDAR and everything is going to be storage. Your typical mission is going to run you anywhere from 10 to 40 gigabytes in size. Okay, so you have all that data you got to shuffle and save.
And how is this horizontal accuracy with LiDAR? How does that compare to
Different animal. Okay, photogrammetry is a mathematical based formulaic model based upon passive light conditions. LiDAR is an active laser source. Okay, so it's using speed of light divided by time to calculate distance. It's shooting out. So LiDAR is shooting out. This particular LiDAR shoots anywhere from 168 to 240,000 active LiDAR shoot points per second. Okay, so it's broadcasting and spraying laser light out. As it bounces off an object, returns and calculates the time for that phase length and says, okay, it's X feet away. As I start building up this point cloud of active light points, it's starting to build the picture. Okay, the only thing that affects LiDAR are things like atmospherics and medium. There's a bunch of stuff that affects the speed of light and through medium, blah blah blah. But at the altitudes we fly, we only fly within 200 to 400 feet. It's like the 15th decimal point, it doesn't really matter. So we're talking plus or minus, it's got a basically a fixed accuracy of plus or minus 3 centimeters. Plus or minus 5 parts per million, and at 200 feet, that's nothing.
Basically independent of your altitude,
Correct.
speed, and
So what we're gonna shoot for the LiDAR instead is density. The lower and slower we fly with the LiDAR, the denser our model becomes. Okay. So it's shooting LiDAR at a fixed pattern, and the forward motion of the drone carries that density with it. So we're gonna shoot, and you'll see as we make models, when we make our model photogrammetry, at the very top of the page, it's gonna calculate our ground sampling distance, or GSD number for us, and tell us where we're shooting at. I guarantee you, basically, you're gonna bring that make mission at 260 feet. It's gonna be 0.99 centimeters per pixel every time, regardless. Now, that does change, because the way the drone works, this is a profile view. If I take off from here with my drone and fly up at 260 feet, and the ground drops away 50 feet, you know, over here, my ground sampling distance is gonna be like more like 1.34 centimeters instead of 0.99. So the terrain is it's gonna average out. There is terrain following capabilities with this drone. I can load in a model so that the drone actually flies in that kind of pattern to try to maintain that if that's important to me. If I'm really shooting for high accuracy. If it slopes away down maybe 20 or 30 feet, I'm probably not gonna get 2 rips. It's gonna be good enough. I'm gonna get an average overall sight ground sampling distance, so I can kind of make a guess on my average overall accuracy. But if I wanted to, I could load in a model, a low density geotiff from like the National Geodetic Survey or USGS as a geotiff, and then tell the software to follow the terrain. It'll be like a 30 meter by 30 meter grid, so it actually may follow like this or something, but at least it'll get closer. LiDAR is just basically the lower and slower you fly. As I make my mission there, I'm gonna get a readout of the density that I'm looking for. I can start pulling out details when I'm doing data extraction, like curve lines and things like that. Like you usually start seeing details at around 450 points per square meter. Okay. The most I think I've ever flown is about 1,800 points per square meter. That was at 125 feet at 4 miles an hour. Typical missions we fly are about 125 to 150 at maybe 10 miles an hour. That's going to give it somewhere around 780, 750 points per square meter. As you fly data, the beautiful thing about the LiDAR is you can fly a mission in 10 to 15 minutes and process it in the back of the vehicle in about 10 to 15 minutes and see what you've got. If that doesn't look good, fly it a second time at a different parameter. Okay. You got a lot of battery and a lot of juice, so I don't know how big the sites you're going to be flying. But there's a lot of weird math that goes behind it, and that's not the purpose of this class. But I do like to make sure you guys kind of understand why we're setting the settings we're setting.
Yeah, that was helpful.
Okay.
So if you, for a project, let's say there's a project for which we want to actually map the elevation level of a terrain.
Mhm.
So we have the road, bridges, ground level and everything.
Mm-hmm.
So it is for flooding comparison, for example.